Now this lecture, or let's say this video, is corresponding to photoelectric effect. Now what exactly is photoelectric effect and why is it of so big of an importance in the field of science? But the fact is, this is the theory given by Albert Einstein, the nuisance in the field of physics. He used to say jokes about it, he used to rebuke mathematicians and whatnot. So photoelectric effect was the first experimental thing which he actually proved, or let's say he actually experimented with or played along with. So apart from being closely associated with Einstein, its major contribution to the field of science is thrashing the idea that light is a wave. So let's see the whole experiment and study the implications through the results and find out what exactly was my photoelectric effect. So let's see what is photoelectric effect. So let's start our discussion of modern physics with the first phenomena which was a breakthrough in the field of modern physics, that is photoelectric effect. So let's start off photoelectric effect. Now, in order to understand photoelectric effect in a much better sense, you need to know the background as well. Now, photoelectric effect was a breakthrough in the sense that it created a doubt in the field of physics whether the light was actually a wave. What happened is there was a fluctuation in the idea of what exactly the light is. Newton said light is a matter, it's a particle. Then comes along Young with his experiment called Young's double slit experiment, which we have done extensively in with chapter of wave optics. That set up the notion that light indeed is a wave. There was no issues regarding that. Now comes along the photoelectric effect, which clearly stated that light is a matter. Now there is a doubt whether the light. I have one evidence which completely suggests, which cannot be proven wrong, that light is a wave. I have another similar characteristic of evidence, cannot be proven wrong, and it clearly states light is a matter. So what should I pick up? So the experiment or the event which clearly stated that light indeed is a matter is photoelectric effect. So that's the background associated with photoelectric effect. So let's dig into it. So photoelectric effect showing the light is also a particle, as I said. Now how does it actually end up showing the light as a particle? We will discuss that. Energy comes in a particle-like chunks, basis of quantum mechanics. So what photoelectric suggested, that is the different interpretation which we can come up with after studying photoelectric effect, is the light is made up of small chunks carrying energy, and that is the basis of quantum physics. So photoelectric effect actually laid down the foundation for quantum physics. Now, energy of one chunk depends upon frequency, and wave-like beam of light has many chunks. Energy of beam is the sum. So, energy which is carried by light can be thought of as comprising of small chunks carrying the energy, and the energy carried by the whole beam of light is the summation of all the energy which is carried by all the chunks. So that is the notion according to photoelectric effect, or let's say the initial version of quantum physics. Now, what are we going to do in studying photoelectric effect? The first point which we will study is, we'll understand this photoelectric effect experiment. PE over here stands for photoelectric. So we will understand this experiment first of all. Then what results you would expect if the light were a classical wave. So I did the experiment, I got the results, and then I will compare it with what would have been the results if I would have considered the light to be as a wave. Corresponding to that, I will have different results, and then I will cross match it. If there is 100% match, it suggests fine, light is wave. If there are some strong opposition with the experimental results and the suggestion, the predictions, then I might have to drop the idea of light being wave. What experiment results it actually did give? So that's what I'm saying. We will sort of predict the results first, then get the results, and then implication and interpretations of the results. The interpretation of the results in context to the predictions as well. We will take predictions into account and the results into account, match them up. and see if there are some clashes or not. So this is a setup, exact setup, and you will be shown a video corresponding to photoelectric effect in coming slides, so as to get the idea of what exactly or how exactly it looks like. So if you notice over here, I have a sort of a wavelength selector. That is, I can select the light which I am actually throwing on the metal plate, and the intensity as well, how many or what is the intensity of the light which I am throwing in, and the battery voltage. So it's like a circuit. So I have three parameters which I can play with: the voltage over here, one, the intensity of the light, and also the wavelength of the light, what type of light I'm actually throwing in. So what actually happened is, I'll give you an event in a nutshell. There are two plates, two metal plates of specific nature. I threw light on one of the plates, and I have connected to the other end of the plates through a wire, which you can see over here. This is the wire. So I have connected two plates through a wire, and the space between them, it's empty. And what I did is I incident a light of specific wavelength on the surface, on one of the surface, and what I observed is current being set up in the circuit. Now that spooks me off. How the hell is the current is able to set up in the circuit, given that I haven't given any sort of power, any sort of EMF, any sort of voltage? So that is kind of spooky for me. And okay, so we came to know, okay, it's spooky. Then what's the reason of this phenomena? I can clearly figure out that light has got something to do with it. The light, when I throw the light is actually, throwing out electrons, because light has energy. It's knocking off electrons. Good, understood. So the electrons are moving in a circuit. Now what I want to find out is it this phenomena, is it being governed by considering light as a wave or light as a matter? That's what I want to find out. Now, so let's move on. Now, what will the setup look like is, we will select a random value of wavelength. Let's say I end up selecting 135 nanometers, kind of a violet or bluish range, and a particular intensity of the light as well, plus the voltage, the battery voltage. So I have 0 volt, 10 volts, infinite volts, whatever. So I end up designing a circuit or picking up some value of the battery, some value of the intensity of the light, and some value of the wavelength of the light. These are the three parameters which I am playing with. So let's start. This is a general setup which I have picked up: 10 volts and particular intensity of light and the wavelength of light. Now I will work out, or let's say dig out, some of the facts, or what are the results which we get. I only end up getting current. So what is the result, or what is the current based on the different parameters? And obviously I will be tweaking with all these parameters. That is, I will changing the wavelength of the light and see what is the change in the current which I get, change in the voltage and see what's the current which I get, change in the intensity of the light and see what's the current which I get. The current is our final result, but I have three parameters which I will be tweaking or playing with to actually observe the dependence. Now, moving on. Now, I clearly know that electrons are being knocked out from the plate. So means I need to give energy to the atom such that the atom lets go of the electrons. Now, the energy which I am dealing with, not in joules. Let's say I don't prefer joules because joules are too big for, when I'm dealing with energy associated with electrons. Because energy associated with electrons, that the energy which I need to get, as you know, it's 13.6 electron volts, close to that. That is the energy which I need to completely knock out an electron from its ground state in hydrogen atom. So this is the energy which I need. Now obviously, if you are in some other atom, you need within this range. So if I try to express it in terms of joule, that is the energy exchange is taking place, it will be somewhere close to the order of 13.6 into 1.6 into 10 to the power minus 19 joules. So it's kind of clumsy for me. It's too big. It's it's hard to handle. So why not I pick up let's say an order of energy which I'm most comfortable with. So that's why I end up choosing electron volt. I try to express energy when I'm dealing with photoelectric effect in electron volts. Now, So this is the convention which we have set up as far as energy is concerned. Then I have also set up the convention, or not let's say the convention, the setup of photoelectric effect, and what are the parameters which I am playing with. Now, moving along. Now this is a swimming pool analogy associated with the setup. Now, let's say I have a calm swimming pool. That is, there's no disturbance in the surface of the swimming pool. Now what I did is, I threw something at it. So what happens? Ripples are created, and the water splash out a bit, right? Now what I did is I designed a pipe. So I have a pipe over here, or there's a funnel over here, which is placed at a decent distance away from the boundary of swimming. My intention is to make sure that the water lands up in the funnel and then passes along like this and it flows out. Now, the only way through which I can deposit the water in the funnel is to create the splash. The splash, hits the boundary and, I create a disturbance in the surface. The disturbance moves, hits the boundary, splashes out and reaches the funnel. Now, I know that I need a decent amount of, disturbance such that the water splashes out to the funnel. Until and unless I am able to create that disturbance, the splashed water wouldn't end up landing in the funnel. So it means I need a threshold, I need a minimum disturbance. I know that if I create a good amount of disturbance, more water will be splashed out. That's fine. But I clearly know that there is a lower limit. That is, if I create a disturbance in a magnitude less than this particular level, I'll end up getting nothing. How much powerful my pump is, that is, it's able to drag the water over here, still can't get it if there is no water landing up on the funnel. So that is what is taking place in a photoelectric effect. You need to give sufficient energy to the electrons so that the atom lets go of the electron and the electron moves out. So this is a real life analogy which you can get inside your head to understand the photoelectric effect. Now, again, it's just written in the words, if no water slops over the side of the pool, you get no flow. Little pump or big pump, still no water current. If electrons stuck inside the metal, no current for the little or big V. Now the same analogy which I said, irrespective of how much powerful battery you end up sticking up to the circuit, until and unless you don't give the required energy which the metal wants to throw out electrons, you won't get any current. That's the bottom line. Put bunch of energy into the water, splash some out, get flow through the pump. Now again, that is what happens actually if you try to be realistic. That is, you end up giving some disturbance. The water splashes out, it reaches the funnel, and the water goes through the pump. Fine. Now if you compare it on an energy scale, you will see that I personally feel that I have given an energy of 10 joules, and corresponding to that, I was expecting this much amount of water to come out, but a less amount of water came out, and that was driven through. So I gave some energy, and the water came out with a particular amount of energy. Now, the energy which I end up giving, is not equal to energy with which the water came out. The reason being, obviously, you need some threshold. You are separating water from the water. That is, you're killing off some bonding. So it means you are sort of separating one part of the system, or let's say one part of the system from the whole system. So you need a decent amount of energy to throw them out. Now, once you have supplied that energy, and the extra energy which you end up giving is directly taken up by, the disjunct quantity, the thrown out water as a form of kinetic energy. So it's like I pay you $10, you take your fee as a $4, and you end up giving me services of $6. It's a simple transaction. So, same analogy. Now, the third point, put energy into metal by heating it very hot, gives electron energy and some splash out. So that's how you end up, analyzing inside your head or visualizing what's going around corresponding to this photoelectric effect. Now, moving on, hot plate. A few electron gets enough energy to just barely splash out. Now, what I am watching for is to find out that lower limit which I was talking about, the energy which I definitely need to chuck out some electrons from the metal. So, that is, I do have a threshold. That's what I want to say. That is, if I end up choosing any wavelength of light, what I observed is for many wavelengths of light, I didn't end up getting any electrons. Now, the moment I hit a lower limit and keep on falling from that limit, because I know the energy is hc by lambda, the energy which I'm giving as a wave is hc by lambda. So, I need to have the minimum wavelength, or let's say, the maximum wavelength, below which if I go, I will definitely get electrons, above which if I go, I am not getting any photoelectrons. So I want to find out the maximum wavelength which is possible for which I get the photoelectrons. So that's one aspect, that is finding out the lower limit. Now, each electron that pops out is accelerated more, so it hits the far plate with higher velocity. So what I have created right now is, if the electrons, they end up moving out, let's say they just barely move out, that is, they just got separated and they are dull, they don't have any energy, because I just gave the minimum amount of energy they need to separate out from the atom. So if I would have given extra energy, they would have some kinetic energy, but they don't have that kinetic energy. So, but what I've done is I've attached a battery to it. So even if they have zero energy, the battery will make sure that the electrons, they are pulled in this direction, pushed from the negative plate, pulled from the positive plate, such that they end up completing the circuit. So it's basically the energy which I leave the particular plate. Let's say I am the electron, the energy with which I leave the particular plate. And if the polarity of the battery are arranged in such a fashion, I'll end up reaching the other plate with a higher energy, the higher kinetic energy. So that's the role of the battery. It will either facilitate the coming of electrons, or it will either restrict the coming of electrons. Now, the restriction can be done by flipping up the battery. That is, the positive side is where the electrons are coming from, and the negative plate is where the electrons are going to. So when you're flipping the poles of the battery, you are sort of restricting the flow of electrons. So again, we will deal with that aspect later on. I'm just giving you the outlook as of now. This is what we end up getting. That is, even if you look at the key points, this, and this. These are the three things which completely blows my mind. The fact is, the voltage is not at all proportional to the current. Okay, the current actually ceases to rise after a particular point. So Ohm's law is strictly not valid for this purpose. The other point is, even if I am giving a zero voltage, I end up getting a non-zero current. Now that's what I was calling it as spooky, how did that happen? And even for a negative, that is, the poles are opposite and now they are restricting over there. So if you look over here, again, if I end up drawing a different diagram, if I'm throwing the light over here and the electron is supposed to come out, so this is a positive plate and this is a negative plate. In this case, the electron will have to do work to overcome this, this restriction, because the positive plate will never let go of that electron and the negative plate will never allow the electron to come near it. So it's actually facing repulsions. So in order to make sure the electron goes to the another plate, I need to give that electron sufficient amount of energy such that it's able to travel through. That's what happens when you apply the battery with the reverse polarity. So this is a positive polarity and this is a negative polarity. That is, in this graph, if you look at it, this is the positive polarity, the one with the previous graph, and this is a negative polarity. So I have shown you the diagram corresponding to the positive polarity and the negative polarity. What happens or what actually is a function of battery when the polarities are flipped. Now, so if the light is, now what I'm doing is I got the results. The results I've shown you, that's pretty evident. This is clear. It's just the result. So you don't have anything to say about it. What we'll do is, we have two versions available with us. One goes with light as a matter, one goes with the light as wave. Based on that, I will try to find out the reasons why I end up getting these results. If wave picture is not able to explain me, then light is not wave. And now if or let's say the wave is if the wave tries to explain this but it fails to, because it comes up with another version or another result, another set of results, then wave theory is wrong, because this is fact, this is what we end up getting, this is the reality. So let's figure out what the wave theory has to say about this phenomenon. Now let's run this through, considering the light is a wave. So if the light is classical wave, predict that just put energy into the plate, it will heat up and you will end up getting the current. That is, wave is an energy, right? So energy is distributed throughout the space. You hit the plate with a particular energy, the light comes out, or sorry, the electrons comes out, and you end up getting the current. Now let's dig into finer details of it, shall we? Now this is the current which you end up getting, right? A typical idealistic one. First, according to wave theory, it will take time to heat up. Right? If you expose it to the wave, if the light is wave, it will take time to heat up, according to wave. So light on longer, it will get more heat, more thermal energy, so electron will come out faster. That is, if I put a light on for a good amount of time, the electrons will come out faster, because more energy has been put. So it will come out faster. And the color of the light, it doesn't matter, because all it depends upon how much exposure I do it, or how much exposure I end up giving to the system. So the color of light has got nothing to do with it. I just know that if I expose the plate for a sufficient amount of time, I will end up getting electrons. If I keep on exposing it to the light, I will end up getting faster electrons. So that all it matters is how much time I am exposing to and what's the intensity of the light. That's the only two things which I am looking out for as far as wave theory is concerned. Now, this is lift which I am actually observing. That is, slowly with the time, the current will increase. Now, the summary of the photoelectric experiment results. Now, the disclaimer is over here, that is, you will be able to play through the simulation, you will be able to have a look at it. So what do we end up getting? Current linearly is proportional to intensity. That is, if I increase the intensity, that the value of the saturation current which you get, the top amount of current which you get, that is this amount of current which you get, it increases with the amount of intensity. So if you increase the intensity, that value of the current increases. So it varies linearly. Now, and another important fact is current appears with no delay. Now this is, you can clearly figure out, it clashes with the theory, clashes with the prediction of wave theory. Current appears with no delay. First clash, we observe the first clash. Electrons only emitted if the frequency of light exceeds the threshold. Right? That is, if the wavelength is short enough. So if it's short enough, you will end up getting the light. Maximum energy that electron comes off with increases linearly with the frequency. So if I increase the frequency, the electrons which I am getting, they have increased kinetic energy. So that's the fourth point. Threshold frequency depends upon the type of metal. Okay, so that's the nature. The amount of energy, the lower limit which I need to remove out electrons, varies from substance to substance. Now, the classical wave predictions versus the experimental observation. Now, the classical, so what we are doing is, now the comparison is done. What do we predict and what do we have? So let's do this. So one given in the black is what we are going to predict, or what we have actually predicted concerning light as a wave, and the red one is the experimental data or experimental interpretation. And we will see if there are clashes or not, and that be important one or not. First up, you increase the intensity, you will get an increased amount of current. Fine, got that. Completely agree with it. So still, wave theory stands true. Second, current versus voltage, step at zero, then at flat. So it's zero, then it's a sudden step, and there's flatness. Flat path matches, but the experiment has a tail of energetic electrons, energy of which depends upon the color. Now the weird part is we end up getting a graph like this, the experimental graph like this. Now I am in complete sync, the wave theory is complete sync with this phenomena, but I am having troubles with this. According to wave theory, I am not supposed to get that. or that tail should remain constant. But I see that that tail kind of changes if I change the wavelength of the light. According to me, this should be the graph for any sort of light which I use. If I keep my substance constant, intensity constant, and I should get this graph. Irrespective of whatever light I use, if I keep the intensity constant, I should end up getting this graph. But what I observed is, whenever I change the value of wavelength, the tail part is kind of fluctuating. I'm getting a longer tail or a shorter tail depending upon the type of the wavelength which I am letting it out or making incident on the light. The plate. So that's the kind of, let's say, a fishy business which I have. So, a clash. Clash number one. Now, color does not matter, only intensity. Now, this is kind of, complete clash. That is, I do know that, I've done the experiment, I do know that it has got something to do with the wavelength of light. That's what actually sets the lower limit. The upper limit. Lower limit is 0, if I'm talking about wavelength. So, it has got something to do with the wavelength, but according to classical wave, the wavelength should have any say in this particular event. So that's clash number 2. Takes time to heat up, so current low and increases with time. So the wave theory predicts that the current should increase gradually with respect to time, because I'm letting light incident on the particular plate, so it will take up energy, get in the heat, then it will accumulate the energy, or let's say the energy increases, and hence the electrons will be thrown out gradually as there's an increase in energy, and hence I will end up getting a steady rise in the current with respect to time. Now, electrons come out immediately, no time delay to heat up. Now, again, the biggest clash which I end up getting is they don't end up taking any amount of time. How small I make the intensity, electron comes out immediately. It doesn't matter how small you end up making the intensity. If they have the energy greater than the lower limit, you will end up getting the current no matter what. So that's the biggest clash which we had. Now, what do we know? So, according to the clash and according to the versions of wave, I should be able to come up with something new. So that's the first thing which I come up new is, if the light can kick out electron, then even the smallest intensity of the light will continue to kick out electron. I just saw that it doesn't depend upon the intensity. It all depends upon a particular wavelength of light. So kinetic energy of electron does not depend upon the intensity. That's simple. If a very small amount of intensity of light is able to kick out electrons, and high amount is also able to kick out the same number of electrons, it doesn't depend upon the kinetic energy of the electrons which are moving out. It doesn't depend upon the intensity. So it means that the light must be getting concentrated or focused somehow. That is, the way the energy is distributed. The reason why the energy takes time, or as the time increases, more energy is deposited, because energy is distributed and it's hitting a particular area, hitting a particular point. So energy is continuously deposited at that particular point. Now, if that's the nature, the current will take more, or the current increases with respect to time. But that's not what I actually saw. I saw current coming up immediately after I threw light at the plate. So it means the energy is not distributed, my friend. Energy is concentrated in some space, or in some object, or in some volume. And when that falls on the object, the electron comes out directly. So, light energy must be concentrated or focused somehow. It's not a wave, it's not spread out, it's there, it's like a capsule, it's in small spaces. Now we'll figure out more about it. At lower frequency, initial kinetic energy decreases and kinetic changes linearly with frequency. This implies the concentrated energy is linearly related to the frequency. Now, this is what I observe. As I increase the frequency, I got more energetic electrons. If I increase the intensity, I should have got more energetic electrons, but I didn't get that. So it means the energy of electrons with which they came out does not depend upon intensity. What I observe later on is if I increase the energy of the light, or let's say decrease the wavelength of the light, I end up getting faster electrons. So it means, or let's say if I increase the frequency, I end up getting faster electrons. So that's the direct correlation that distributed, or let's say the focused concentrated energy directly depends upon the frequency. And the kinetic energy of the electrons which I am getting also directly depends upon the frequency. So that's the correlation which I actually established. Is minimum frequency below which light won't kick out electrons. Now, as I said, this is what we observe. So it means need a certain amount of energy to free electrons from metal. So it means that the packets which we are dealing with, the concentrated focused energy which we have, that energy should be greater than what's required for an electron to come out. If that's not greater than that, the electrons won't come out. The photoelectric, what Einstein said, you need a photon picture of light to observe, to explain this observation. The photon coined by Einstein is basically that focused concentrated packets which he's dealing with. So the focused packets, they are called as photons. So what he said is light, they come in chunks, and that chunk they are called as photon, chunks of energy. A photon interacts only with one single electron. This is what he said. That is, light comes in chunks. A photon interacts only with single electron. Third, the photon energy depends upon the frequency of the light. That is, he just described the things which we just discussed. He put a name to it that this is photon. And the rest of the properties are exactly the same. Now, here is an analogy, again a different analogy which might help you out. Light, like a kicker, puts an energy, all concentrated on a ball or electron. Blue kicker always kicks the same and harder than the red kicker always kicks. So the blue kicker, let's say the guy over here is a light. So if I have a blue light, so it kicks harder than the one I have with the red kicker. So kicks energy, top ones get out, bottom ones they don't. Harder the kick, shorter the wavelength, more get out. So it's like this. It's tough. So it kind of moves out. So it doesn't go, it moves in. So that's the nature which I have. So what we observe is in the ball and the person kick analogy, the man over here is the kicker, called the kicker, is a light. And the electrons, they are put in a well of a particular height. In order to make sure that the ball ends up rising to the well or to this dump, I need to kick hard. So if I'm kicking hard enough, the ball will end up rising. Now if I kick up a bit harder, the ball will rise to the top with the particular energy. That's the same thing which we have. If I give the metal the sufficient amount of energy, it will sail through, or it will come out of the atom. And if I am given more than what's required, it will consume, or the part of energy which will be utilized by the atom have to be given to the atom, and the leftover will be taken up by the electron as its kinetic energy and move with that particular speed. So that's what is written over, that the kinetic energy with which the electrons come out is basically the kick energy, the energy with which I kicked minus the mgh. Over here, this is the speculation, or this is for the ball and this is for the electron. H nu is the energy with which I kicked. Phi is the energy which I need to make sure the electron just comes out. And half mv max square is the energy with which it comes out. So I need a particular amount of energy given to the atom to release electron, then the leftover energy is used as a kinetic energy. So that's the expression. Now remember, whenever an electron comes out, it undergoes collision within this neighborhood. So the moment it comes out, it follows this. So imagine a scenario like this. I'm a guy who comes up to you and I said, take this much amount of money, take $100, and you have a product which values at $30. What you will do is you will give me the product and 30 or let's say 70 rupees of deficit with me. Now let's say the product is a phone, right? I'm buying out a phone from you. What I did is I ended again giving you $100. What you did, you didn't give me anything. You actually end up giving me the phone with a credit balance of $70 in it. Now that's the same transaction which I have. I gave a particular amount of energy to the atom. Atom didn't end up giving me any energy back. What it did is it gave me an electron, and the energy which was required for robbing an atom of an electron, that was taken up, and the leftover was given to electron as its kinetic energy, and the electron moves out with that deficit energy. Now usually when the electron moves out, it has that much amount of energy, but because of the crowding, it collides with other atoms. Electron collides with the other atom and it decreases the energy. So whenever there is a photoelectric effect, I will end up getting electrons from zero energy to this maximum possible energy. So I will end up having some, let's say, some fellas with this much amount of energy who are totally undisturbed. But those who are kind of disturbed will have an energy less than this. So I have a whole band of energy from zero, electrons from zero energy to this much, the maximum kinetic energy which is possible. Now that's the reason why I have these cells attached to facilitate their movement, such that each electron is pulled. Come on, you lost some energy because of collision, don't worry, I will help you out, reach to the other shore. So that's why there is a battery with a particular polarity. Now there are different substances which depends upon, or let's say they are separated based on the energy which I need to knock off an electron. So sodium is actually easy to kick out. The sodium electrons are easy to kick out than the case of the platinum. So it means one has a smaller work function and the other one has a bigger work function. Work function means I need to do some work, make sure the electrons are popping up. First, effect of intensity of incident light on photoelectric current. That is, what will happen if I change the intensity of the incident light on the photocolor. Now, this is the graph. It increases. As discussed, increase the number of photons. More photons will hit more number of electrons. More number of electrons are in contact with the photons. More number of electrons will be released. More number of electrons are released. More is the current. Simple analogy. For a fixed frequency, the photoelectric current increases linear with the increase in the intensity of the light. Second up, effect of potential on a photoelectric current. Now, what will happen is, if I throw in that, now for analyzing this setup, just keep in mind the circuit which I have, right? The same circuit which we had over here. This is positive, this is negative, and the light is thrown over there. Now, if I want to make sure that the electrons are able to reach on the other end, I should be able to facilitate the movement. But in this case, it won't. The electrons will find it hard to reach over there because I am opposing the flow of electrons. So, if the potential difference is large enough such that the most energetic electron is also not able to make it to the other end, I will end up getting zero current. Zero. Because I have a whole range of electrons starting from 0 to h nu minus h nu naught energy. Electrons are from this value to this particular value. Now, if the potential difference V, the power of the battery is such that even the most energetic electrons are not able to make their way to the other end, I get zero current. Now, slowly, if I am, let's say, decreasing the power of this polarity, I'll end up getting a current. As soon as this value hits 0, I'll end up getting these values of current, depending upon different values of potential. As I keep on increasing the potential, there is a rising. That is, right now I'm in this half, I became an helper. In this half, I'm an opposer to the flow of electrons. So that's what I'm actually end up doing. So saturation current for a fixed frequency and intensity of light, the photoelectric increases with the increase in the positive potential applied to the anode. Now, when all the photoelectrons reach the plate A, current becomes maximum and is known as the saturation current. Now, many of the electrons are actually knocked out. So, few of the electrons will be able to make to the other end. If, let's say, there's no potential difference applied, now those who are having zero energy, they won't be able to make it to the other end. So, I have a fraction of electrons, successfully making a transition from one plate to another plate. But if I sort of help with a particular polarity, if I help the movement, then more number of electrons will be able to make it to the other end. Now there will come a voltage corresponding to which all the electrons are able to successfully move it to the other end. And if I keep on increasing the voltage from that point onwards, the current won't increase because I'm successfully transporting all the electrons which are created, which are thrown out, which are free from one end to the other end. Irrespective of how much voltage you increase, they're just reaching faster. Or there's not an increase in the number of electrons reaching over to the other end. They're simply reaching faster, and that's just not of issue for me. That doesn't affect the current. So that is the saturation current. Second, when the potential is decreased, the current decreases but does not become zero at zero potential. We just discussed that because few of the electrons, they do have a sufficient energy to make it to the other end. So the energy is, or let's say the current is not zero. Now this shows that even in the absence of accelerating potential, a few photoelectrons manage to reach the plate on their own due to their kinetic energy. As explained, it's written over there. Now, when negative potential is applied to the plate A with respect to C, photoelectric current becomes zero at a particular value of negative potential, called the stopping potential or the cutoff potential. Now, here is a very beautiful fact. That is, the electrons, they are not able to reach to the other end when the polarities are simply reversed. That is, if this is the case, electrons are coming out, or they're trying to come out and move in this direction. Now the electrons which are coming out, they're having an energy between this range, h nu minus h nu naught. Now the fact is, they're not, if I apply the particular amount of voltage, they won't be able to come out. That is, given this energy, given this potential difference, this barrier which is opposing the electron flow, it's sufficient even for the fastest moving electron. So even if the fastest moving electron is not able to reach it to the other end, it means no electron will be able to reach to the other end. Hence the current will be zero. So that is cutoff potential or stopping potential. So you can literally figure out that the stopping potential kind of depends upon simply the stopping potential. Let's say this is the stopping potential, simply depends upon the type of wave light which you are throwing at. It doesn't depend upon how fast or what is the intensity of the light. It simply depends upon the quality of light, the wavelength of the light which you are throwing in. Effect of frequency of incident light on a photoelectric effect. Now, for a fixed intensity of incident light, the photocurrent does not depend upon the frequency of light, because the photoelectric current simply depends upon the number of photoelectrons emitted, and in turn on the number of photons incident and not on the energy of the photon. So as clearly stated, if I want, let's say if I increase the frequency or decrease the frequency, if I'm, let's say if I'm changing the frequency within, let's say above the minimum frequency which I need, let's say nu minimum is the frequency which is needed for setting up a photoelectric current. Now if I am playing at a particular frequency which is greater than this minimum frequency, and I'm fluctuating, I'm changing the frequency, still the electrons will come out and the same number of electrons will come out. If I want to increase the current, I want to make sure that the intensity is increased, because if the intensity of the incident light is increased, means more number of photons are now hitting the plate. If more number of photons are hitting the plate, it means more number of photons are coming in with contact with electrons. If more number of photons are coming in contact with electrons, more number of electrons will be ejected out. As simple as that. That's the regression which we follow. So frequency has got nothing to do with the current. Okay, just got nothing to do with. That is, I'm talking about the frequency greater than the minimum frequency. Now, for the fixed intensity of incident light, the photoelectric current increases and is saturated with the increase in the positive applied voltage to the anode. Again, the same notion which we have, just depicted it over here. Now, the photoelectric, what we're trying to do is, if nu2 and nu1 corresponds to different types of light incident on it. Now remember, this shows that I have the same intensity of light. I have the same intensity of the light. Now one stopping potential is greater than the other. That is, I need more negative voltage to stop the current in one case and less negative voltage to stop the current in the other case. It means, as I said, given over there, that is, it depends upon this. The stopping potential depends upon this. So it means Vs2 is having a higher frequency than Vs1. That is stopping potential corresponding to nu2 and nu1. That is, nu2 is greater than nu1. That's what we can conclude with this. This is the effect of frequency of incident light on stopping potential. Okay. However, the saturation current is same for different frequency of the incident lights. When the potential is decreased and taken below zero, photoelectric current decreases to zero, but at different stopping potential for different frequency. Again, we have discussed all these points before, so it's just stating out the obvious. Just make sure that you are not bothered by the different comparisons which we have done. Make sure wavelength, intensity, voltage, how these parameters affect the photoelectric current. If you get the total phenomena inside your head, irrespective of whatever comparison which I am trying to do, it's easy for you. So the students, they end up making mistakes because they juggle things up. They are exporting one concept from the other, then to the other, so it all gets mixed up. How is the dependency of intensity on photoelectric current? You are quoting something different. So please don't do that. Make sure you have understood this properly, this photoelectric effect. Okay. Now, threshold frequency, again, minimum number of frequency which I need to make sure the photoelectric current is set up. Now, the application of photoelectric effect, these are the things which it's used in: automatic fire alarm, burglar alarm, scanners in television transmission, reproduction of sound in cinema film, paper industry to measure the thickness of paper, to look at the flaws or the holes in the finished goods, in astronomy. So just make sure you go through all these points, and because it will be very extensive if I start discussing each and every importance or how photoelectric effect is kind of used in these kind of devices. It will be very extensive. So again, automatic switching of street lights, temperature control, photometry, beauty meter. You might have seen in models or in actors, they bring up a meter over here and they click it, and the reading says 11.2, 11.3. That is how bright are you. So they measure it because the radiation which you are throwing in, it's received on this particular device, and it sets up a current. Corresponding to the current, the rating is done. If it's a good amount of current, okay, 11.2, 10, 2, 9, 7, something like that. Light meters used in cinema industry to check light, again a different version of the same instrument. Photoelectric sorting, photo counting, metrology. So now that we have studied about photoelectric effect, so why not we actually put every concept, every new fact which we have learned about photoelectric into a particular simulation and see how things pan out or see how things actually look at it. Now over here I have the actual setup, that is I have a source of light position over here, and this is a plate, a metal plate which will throw out electrons when the light is incident on it. Obviously I do need a particular wavelength of light to eject out electrons out of it. And this over here decides the intensity of the light which will be falling on that particular plate. So right now it's set to 0%, that is no incident light is thrown on this particular plate. And this decides the frequency or the wavelength of the light which I'm going to throw. Right now I've set at I'm trying to set at 400 nanometer. Okay, this looks good. 403 now it's fine. So it's presently set at 403 nanometer, and I have the whole range of light rays which I can throw at it. Over here it's connected to a battery. Right now the battery is set at 0 voltage. Now electrons are moving from this particular plate to this particular plate. So if I sort of eject a positive voltage, it means this becomes positively charged and this becomes negatively charged. So I will be facilitating the flow of electrons in this direction. That is, greater the voltage, faster will the flow of electrons be towards the other plate. And completely opposite will be a negative voltage. That is, this is a positive plate and this is a negative plate. Now when the electrons are coming out, they are being repelled and attracted. Repelled by this particular plate and attracted by this particular plate during the motion. So it will be very hard for them to actually make it to the other end. It depends, obviously it depends upon the voltage which I am supplying. So again, let's get back to the default setting of 0 volts. Okay, let's hit 0. Okay, let it be around 1 or 0.2 or something like that, minus 0.2. Now over here I have three graphs, current versus battery voltage. There is a current which I will observe. This is the reading of the current you can easily see over here, and this is a battery. So the first analysis which we will be doing is current versus battery voltage. The second being current versus the light intensity over here. Third will be the electron energy versus the light frequency. Now we know that for photoelectric effect to take place, I do need to throw out light at a particular wavelength, and the energy which it carries should be sufficient to throw out electrons or remove electrons from the particular metal of interest. Now let's start off the experiment. So I am slowly increasing the intensity. So right now I have set around 50%. I am trying to set around 50%. So for 50% of intensity, UV rays, I see that there is just a small amount of current, right? And you can see the motion that this is a negative voltage. Negative voltage is applied, so it means this is positive and this is negative. So many of the electrons, they start off good, but they are slowed down and they move back. And few of the electrons, they actually make it to the other end. So if I increase the negative voltage, meaning this will become more negative and this will become more positive, they hardly come out, but they simply go down. See, continuously increasing, they just barely come out at -7 volt. See, the current is almost negative. It's like current is moving in this direction, and sorry, current is just negative and it's 0. Again, let's increase the voltage. Now if I increase it, again they are facing a bit of difficulty. It's -0.2. Now if I increase it, you will see that they will be facilitated. They're coming out slower and hitting faster. Coming out slower, hitting out faster. So let's decrease the voltage to observe it in a better way. So they're coming out very slow and then they're getting pulled in this direction. So the current is sort of increasing as I'm increasing the battery's voltage. And if I increase the intensity, now I'm increasing the intensity to 50, let's say I hit around 90. So I will have more number of electrons coming out because more number of photons are actually getting incident on the particular plate. What about the wavelength? Now if I, and why I'm doing the tampering with intensity, wavelength of the light, the battery voltage, please also have a look around the graphs as well. So if I'm increasing the wavelength, you see less number of electrons are coming out, because as I'm increasing the wavelength, actually the energy of the light which is falling on this particular plate is decreasing. As it's decreasing, it's getting below the threshold energy. So still no ejection of electron, still no ejection of electron, still nothing. What I'm trying to do is look at the point where I do see ejection of one electron. Just one electron will do. See, around 500 nanometer, I end up seeing the ejection of electrons and starting taking place. It means that I have just reached the threshold energy. It's around 520 nanometer, I guess, around that. Around 530, still the few of the electrons are coming out, even though it's 0 voltage. So it means I need to increase slightly. Yeah, so it's around 535 nanometer. That is the threshold energy of this particular plate. That the electrons will start to come out when I decrease just around 538. I can definitely say that's the potential. Hc by lambda. Lambda being 538 is the work function. Now if I keep on decreasing it, that is increasing the energy, more number of electrons will come out. See, I'm increasing the energy, so huge amount of electrons are coming out. And also, please have a look in these three graphs as well. Current versus intensity. Intensity is remaining constant, but the current will shoot up. See, the current will shoot up because energy of the light which is falling is increasing. Current versus battery voltage, again it will shoot up because I'm not tampering with battery voltage, but even though I'm getting more current because more number of electrons and faster number of electrons are coming out. And see, there's a steady rise over here. Electron energy versus light frequency. This is how you can actually visualize photoelectric effect. Let's try out a problem on photoelectric effect. So the question goes like this: photoelectric threshold of a metallic silver is lambda is equal to 3800 angstrom. Ultraviolet light of lambda 26 angstrom is incident on the silver surface. Calculate first the value of the work function in joule and in electron volt. Second, the maximum kinetic energy of the emitted photoelectrons. The maximum velocity of the photoelectrons. I know that the work function is h nu naught, which in turn is equal to hc by lambda naught. So just putting out the value, 6.26 into 10 to the power minus 34. The value of speed of the light is 3 into 10 to the power 8. And lambda naught is given to be 3800, which comes out to be 5.25 into 10 to the power minus 19 joules. So this is, so make sure you carry out this calculation. You will end up getting 5.25 into 10 to the power minus 19 joule. Now if I want to convert this in terms of electron volt, this will come out to be, let's say this is equal to 3.25, I guess, close to this electron volt. So this is the threshold energy which I actually need. Now, if I want to work out let's say the amount of energy which I am throwing it with lambda is equal to 2600, it will be equal to similarly h nu hc by lambda, and over here I will have 6 into 6.26 10 to the power minus 34 3 into 10 to the power 8 divided by, and I have 2600 angstrom and I'm dividing it by 1.6 into 10 to the power minus 19 to make sure I'm dealing with, I'm not getting clumsy with them or the energy which I'm dealing with. I want to make it short and sweet actually. So H nu, that is the energy which I'm throwing in, is equal to, if you work this out, you will end up getting close to 4.75 electron volts. So that is the energy which we are throwing out on the silver surface, and the energy needed for knocking off the electron is 3.25 electron volts. So the maximum energy of the electron which I have is 1.5 electron volt. The maximum velocity which the electron has obviously is half mv square, 1.5 into 1.6 into 10 to the power minus 19 joules. That's energy. So the velocity will come out to be 3 into 1.6 into 10 to the power minus 19 divided by 9.1 into 10 to the power minus 31 mass of the electrons. So again, if you work this out, you will end up getting close to 7.2 into 10 to the power 5 meter per second. So imagine how quick the electron moves once it gets knocked out, or the maximum, or let's say the electron with the maximum energy. This is how much fast the electron moves around this range, from 0 to this much speed of 7.2 into 10 to the power 5 meter per second. So the key points which you should note after studying photoelectric effect is, how did the photoelectric effect shatter the idea of light being wave, and how it actually established the idea that light indeed is a matter. Now, as I told you in the video itself, there is a clash between light as a wave and light as a matter. So make sure you are comfortable with both the ideas as a whole. Light as a wave, YDSC, light as a matter, photoelectric effect. Two supporting evidence for two different theories. Now, just stick to those versions and treat them separately, not simultaneously. That's the key point. I repeat, they are separate, not simultaneously. Now, let's move on to the next, let's say the next phase of modern physics. Let's see what we have in the next phase. Stay tuned.